Good morning, everyone, and welcome to our series of technical presentations. This is our fourth presentation on electromagnetic transient study topics. I presented the first three webinars, but today I will be making an introduction on the topic of simulation, modeling, simulation and modeling to facilitate offshore wind and HVDC systems. So I will make an introduction to the topic, and my colleagues Farid Mosalat and Randu Gunasekara will join in to show some demonstrations, and Farid will be discussing specific technical details on modeling and some simulation experience that we have come across over the last 5 or so years. You can say offshore wind facilities are special designs. For one, they are offshore, right? So the construction is difficult. You don't want anything to go wrong, because if things go wrong, it's difficult to maintain, difficult to repair, and so on. And also, if you have a wind farm offshore, it's likely to be a large wind farm, maybe 500 megawatts or more. Like there are offshore wind farms that are 1000 megawatts in size. So you want to make sure that your design is right. So that's one of the reasons why you want to do detailed studies using PSCAD. And we have seen pretty much every offshore wind farm that is being designed or in operation went through a detailed EMT study process. So in today's webinar, I will provide a brief overview of what is involved, the general layout, the collector systems, equipment in the offshore substation, the cables, the HVDC converters. I will give you an overview, and I will discuss very briefly how different components are modeled in PSCAD, to what level of detail you have to go into in order to get reliable results. After that, we will give you a live demonstration of how you may, one thing is, before you do the study, you have to develop the PSCAD model, which includes the AC system transmission network. So we will give you a quick demonstration of how you can convert your existing databases in PSSC or dig silent form into the AC system model that you want to represent in PSCAD. This will take about 10 minutes. My colleague Randu will provide that demonstration, and then I will hand over the presentation to Farid, who will go through some detailed technical discussions. At the end, we will show you two examples. One, where the wind farm is connected to the grid through an AC cable. Two, where the wind farm is connected through HVDC links. So that's the plan. This is what, schematically, this is what the an offshore wind installation looks like. The wind turbines are connected to the offshore substation through a network of collector cables, 33 kV or whatever. You can see it right here. There may be number of feeders. In this case, I have shown 5 feeders going out from the offshore substation. Then you have the offshore substation equipment. Transformers are probably the most critical pieces of equipment, but you will also have other equipment such as filters. You need shunt reactors, because these cables generate a lot of capacitive reactive power. If the wind farm is producing a low level of power, then these cables are not highly loaded, and then they will under that condition they will generate a significant amount of capacitive reactive power. When the cables are fully loaded, not so much. So you need to have reactors to compensate for the capacitive reactive power, but probably just fixed shunts are not sufficient. In most cases, fixed shunts are not sufficient. You need to have some form of dynamic reactive power uh, compensation, STATCOMs or SVCs. So they will all be uh, connected either to mostly to the offshore substation. So all these must come into the picture. Then you have the export cables like 50, 60, maybe 100 kilometers long in some cases, because the onshore connection point may not be right at the shoreline. It may be further down into land. So these cables could be pretty long, and they do introduce certain resonances network characteristics. So they have to be modeled in adequate detail to get reasonable results. This is very similar. It just shows that the only difference here is now the power export is through HVDC. So you have to have the onshore and offshore converter stations. And now the HVDC is based on VSC, MMC technology, but the rest probably is similar. You probably don't need filtering and SVCs as much as you do need them with AC connections. So we already discussed why we need to perform detailed studies. Large capacity of these wind farms. You have submarine cables, which introduces net resonances and network characteristics that you need to consider in the overall design. And like I said, if things go wrong, like it's difficult to maintain, repair, so you want to make it right the first time. And also, unlike in an onshore wind farm, where typically all turbines are provided by a single vendor, in a large offshore wind farm, it is possible that multiple vendors provide turbines for different feeders, different clusters. So the coordination of multi-vendor equipment is also critical, and that you have to study. You have to study that to make sure things will work well in a coordinated manner. Then you have the long AC cable. It's possible that the AC connection point is weak. Then you have all the weak grid connection related issues that you have to take care of. So quite a few of the challenges with offshore wind farms are similar to what you would face with when interconnecting onshore wind farms or solar PV. But there are some very specific challenges as well. Like I explained, the cables may introduce specific network resonance. In the case of the HVDC connection, you will note that on the offshore side, you only have inverters. There are no synchronous machines. We know that inverters, the way we have been typically the inverters follow the grid, but here you don't have a grid, like you don't have synchronous machines. So again, the control design is different and specific. So this needs to be studied. The type of studies, I categorized them I listed them in two categories. The fast transient studies for equipment design, right? Like transform energizing. Now you have to energize the offshore transformer through a long cable. This could give rise to resonances. The cable connected to shunt reactors is known to give low frequency resonance conditions. You have to study them. Then cables, when energizing, when the cables are connected to shunt reactors, when you're energizing, you can have this phenomena called the zero missing condition. These must be studied using PSCAD, but today we are not going to focus on that. we are going to focus on more system level studies, the dynamic response, right? You have to make sure that your wind farm meets grid code requirements, like providing the required voltage support, frequency response, fault current contribution as described or as requested in your grid codes. Then it is very common that you have to study the dynamic response following disturbances like faults. Control interactions with other devices, other dynamic devices like generators in the system must be studied. Then one specific condition that you study with offshore wind farms is what would happen if there's a fault in the collector system? What would happen if there is a fault in this collector system and one of the feeders, or maybe one or many of the feeders, trip? If a feeder trips, what happens is these wind farms or these wind turbines gets isolated from any external connection. They're just connected to a system of cables, right? So if the wind farm controls don't react to this condition correctly, there is a risk of severe sustained over voltages in this part of the isolated feeder, which could seriously impact and damage equipment. So these are some of the items that you study with PSCAD. I think I explained this, I discussed this. Like what I am showing you here is a schematic representation view of the onshore grid, right? What I'm saying here is, like, you have the two cables coming into the onshore substation, and near the connection point, you can have other wind farms, other HVDC connections or power electronic connections. You are likely to have synchronous generators. So one concern is, would this wind farm, the operation of the wind farm, interact in a negative manner, uncoordinated manner with these other devices and cause control interactions? One other concern is that we typically look at, would this new addition of a wind farm, offshore wind farm, impact the mechanical oscillation of the existing generator shafts, torsional interactions? So these are some of the items that you would study. Like, I don't want to go into, we discussed this in our last presentation. We don't want, like, when following a fault or a disturbance, we don't want the system to go into, or the inverters to go into these type of uncontrolled behavior, control interactions. Now, let us talk a little bit about model development and the data that you need to represent the wind farm and the surrounding AC network in PSCAD to perform these studies. The cable, we said, can introduce resonances. So it's an important part of the whole arrangement or the installation. So you have to first model the cable accurately. Like, these are the types of cables that you can have, like coaxial single cables. So you will have 3 of them in an AC connection, or you can have all three cables in a pipe type arrangements. The vendor will provide you their data sheets, and you have to extract the necessary information from the data sheets to represent in a PSCAD model. Some of the data items that you need in the PSCAD model are straightforward to derive from these data sheets, and in some cases, for some data items, you will have to go through some data conversion. But at the end of the day, you have to extract the available information and convert it and make sure that your at least from a 50 hertz or 60 hertz point of view, the RXB values of PSCAD matches what is given in data sheets. This is not always very straightforward, but because of the criticalness of the study and the design, we encourage our PSCAD users to come to us and get help from our technical support team when they have to make these type of conversions and cable modeling. Then let us see what we have to do to represent the collector system. In an offshore wind farm, you can have hundreds and hundreds of turbines, maybe turbine units. And for system level studies, you don't have to model, we don't model them one by one or individually. We aggregate the wind turbines. So there are different options available, different strategies adopted by different people. Like it's very common to aggregate all of these wind turbines as a single aggregated wind turbine unit. So you represent, let us say there are 100 turbines. You represent them by a single vendor provided wind turbine model and scale it by 100. Okay. Another option is to aggregate them on a feeder basis. So you will represent the wind turbines on this feeder by a single unit, scale by the number of units on this feeder, and same for the other feeders. So these are two common approaches. Most of the time, what I see is for typical system level studies, single aggregation works. The other question is there are a number of cable segments that connects different turbine units, right? Here's a typical arrangement. How do you represent the collector cables, right? So again, when you are equalancing the wind turbine, you have to find a strategy to aggregate the cable as well. So this paper from NRail, which was published a number of years ago, is a very good reference. And over the past 5-6 years, we have been following the method. It's pretty simple to follow the method described in this paper to aggregate these cable sections into a single equivalent cable. If you follow this, you will make sure that the cable impedance, equivalent impedance, the reactive power consumption of the cable, generation of the cable, and some harmonic impedance characteristics can be maintained compared to the actual practical implementation. So once the equalancing is done for cables and aggregation for the wind turbine generators, this is what the model would look like. A single scaled wind turbine model connected to the equivalent cable and then connected to the bus bar. And like I mentioned, you have to model the offshore station equipment such as filters, shunt reactors, transformers, HVDCs, and STATCOMs. And the wind turbine model itself, the wind turbine itself should be or must be modeled, in my opinion, our recommendation, or just model it with the vendor provided model. Like if you are doing such a specific study, generic models will not work. You may be able to use generic models for some of the other units further down in the network, but your specific interest is this particular offshore wind farm. For that, you definitely need to obtain the model from the vendor. And even with the other equipment on the offshore stations, such as HVDC STATCOMs, as much as possible, use the vendor provided model. So we talked about the cable system aggregation, we talked about the offshore substation equipment modeling, the wind turbine modeling, cable modeling, and then finally we come to the AC system, the onshore grid, right? So one of the things that we are looking at is how the new wind farm and the cable system or the HVDC would interact with the rest of the system. So you have to model the rest of the system in adequate detail. Typically, our experience, we typically model 4 to 5 buses or 4 to 5 to 6 buses away from the onshore connection point. When you go 4 to 5 to 6 buses from the connection point, that would cover actually a pretty significant part of your network. You have to decide how far you want to go based on engineering judgment. You have to look at what other devices are connected in this system. There could be other wind farms, fax devices, other HVDC connections, significant HVDC connections, other generation nearby. And after reviewing your network information, you have to decide how far you want to go. Okay, so this could be a time-consuming task, right? You typically have your network information in PSSC, dig silent or similar format, and now there are methods to convert the information directly into PSCAD. So ETRAN is one option that you have had for many years. Today, very quickly, within 10 minutes, we are going to demonstrate a tool called PrSim that you can use to convert PSSC and dig silent power factor data. You can convert the network data, the RXB values of lines, transformers, and so on, as well as you can convert the dynamic data of generators directly from these databases, PSSC or dig silent, into PSCAD. Of course, your generators may have non-standard or non-IEEE type exciters and governors like custom design, in which case direct conversion is not possible. You have to develop these models manually based on the block diagrams of the control systems. So with that, I'm going to pass the presentation to my colleague Randu, who will very quickly demonstrate how to develop the AC, how you can develop this AC network. She will show you two strategies where you will draw the network and convert it to PSCAD. Number two, most of the times, system operators, utilities, you already have the single line drawings of your system in PSSC or Power Factory form. In that case, you can directly convert that drawing and the data into PSCAD without you having to manually go through the single line drawing process. So we will demonstrate that, and Randu will also briefly talk about the model validation process, and then I will hand over the presentation to Farid to go through the technical details of offshore wind and HVDC studies. So with that, please welcome my colleague Randu and then my colleague Farid into this series of presentations. Randu, it's yours.
Hi. Okay, as Darshana mentioned, in order to convert a transmission network database to PSCAD, we use the software tool called PrSim that was developed at MHI. I hope you all can see my screen. So
not yet.
Oh.
Or maybe I'm not looking at. Okay, yes, please, sorry.
Okay, so this is how PrSim looks like. Usually when we are asked to perform a study, we receive the network data in PSSC or dig silent or in a similar data format. So we can use a program like PrSim to convert this data into PSCAD. So for the demonstration purpose, I've picked an example network database that is in PSS data format to demonstrate you how to do the model development. So let's start developing the network. I have already created the file in PrSim called AC network. So you can import the raw data file by clicking this tab. And if you have sequence data, dynamic data, or location data, where you can save the XY coordinates of your single line diagrams if you have, and load it to this tool. So you already know the point of interconnection where you're going to connect your wind farm. So we'll start from there. In this particular case, I have picked bus 105 as my interconnection point, and I've already loaded the raw data file. So just for the demonstration purpose, I'll just develop 2-3 buses away from the point of interconnection. So I'm going to expand the bus. So this is the bus I picked. So here I have developed just 2-3 buses away from my point of connection, but you can develop the network away from your point of connection as many buses as you want. You can convert this network just by 2 clicks. First, export the data. So what you see is the develop that you will be seeing in PSCAD, and I'm going to convert it to PSCAD. Okay, so this is the PSCAD network model of the case that you just built in PrSim tool. So the buses that are highlighted with these boxes are the boundary buses. And this is the Thevenin equivalent network model that represents the rest of the network that was not developed in the study area. And to show you, I have already converted a PSCAD case where a larger area is developed around the point of interconnection. This is related to the same case that I showed you before. And I will show you another easy method to convert network data using PrSim if you have the single line diagram already developed in PSSE or DigSilent. So I have created a file in PrSim called AC Network 1, and I have imported the raw data file and the location data file. So as you load this network data, you will be able to see if it is properly imported in these tabs. So as you can see, the network data is imported. I will show you the single line diagram that I had already developed in PSSC. So once I loaded the location file where you have the XY coordinates of that single line diagram, I can simply expand the network in PrSim. So this is exactly similar to what you saw in PSSC. And as I explained before, just by 2 clicks, you can convert it to PSCAD. So I'm going to export the network. and send to PSCAD. So this is the network model you saw earlier, and the rest of the network that wasn't developed is represented using Thevenin equivalence, this network equivalent component. So in order to validate this transmission network, you can check the power flows at different locations in transmission lines and power injections from the generators. And you can check the fault levels at different buses in different locations and match with the corresponding data in the PSCAD network original file data. So if it is a good match, you can assure that your model is ready for the study and it's properly validated. So I'm going to hand over this to Farid or Darshan.
So, hello everyone. Thank you for joining this webinar. I'm going to switch to kind of a different topic, not in terms of the types of wind turbines, and some observations from some real projects that we have been involved in. And we thought maybe this is somewhat helpful for you to see what to expect when you do studies in PSCAD. And these are real projects because in addition to developing software programs like PSCAD or PrSim that Rander just showed you, we also have an engineering team that works with colleagues like you. We might already have worked with you on some of your projects. These are our involvement in real projects and some of the observations that you could expect in such studies. As an introduction to the rest of the slides, it's just a refresher and reminder of the types of common wind turbine generators that are used in offshore wind. We are dealing with large units. Most likely they are nowadays type 4 based on full converter-based system. And then we have been involved with projects with type 3 as well, even in offshore. The common thing in these types of turbines is that most of them right now are working based on grid following requirements, meaning that even though the controls are trying to regulate active and reactive power levels at the point of interconnection to the AC source, they all use a synchronizing mechanism called the phase lock loop. Whether it's an induction machine where they're in doubly fed or type 3 scheme, where you have also an electric connection to the machine terminals, the power electronics, and the controls that are required for the rotor side currents and eventually active and reactive power regulation, they use a phase lock loop. Also for type 4, which you have basically a full converter-based link between the generator and the grid, there is a phase lock loop in order to synchronize the controls inside the grid side converter and the network. Of course, there are pushes to move towards grid forming, especially for larger scale in the future, where you might have to emulate the behavior of a synchronous generator and try to energize a network, and even the machines work together in a more coordinated and you would avoid the problems that we have been facing in the industry with weak grids and PLL robustness. Then most of, in addition, in contrast to that, the grid forming ones, the grid forming units that have been used and are being used currently in the industry, they use the phase lock loop concept. So for type 4, I'm focusing on type 4 and showing some block diagrams as a reminder to you that you could have there are basically, as you saw, there is a grid side converter and there is a grid generator side converter. The generator could be permanent magnet without the gearbox, or even an induction machine squirrel cage, and you have a full converter base between the two. But the modes of operation, the modes of controls for these two converters, you have two basic options. The grid side converter, commonly most vendor schemes, they control active and reactive power, whereas the machine side converter regulates the DC voltage. There are some vendors that do the opposite. So you basically, on the grid side converter, you have DC voltage control and power and AC voltage control on the generator terminals. So if you consider the second option, many vendors use the DC voltage control on the grid side converter. And there is also a ballast load, or we call it the dynamic brake system, or the DC chopper on the DC link, so that if there is any transient imbalance between the power, for example, by the time the machine side converter tries to regulate the power in case of an AC fault on the grid side, that excess power has to be dissipated in load in order to prevent the DC voltage from rising beyond the acceptable values. And that is the role of the DC chopper. But in order for the converter, the grid side converter, to operate correctly, we are always relying on the basic concept of active and reactive power regulation for a voltage source converter. We need a reference voltage, which is the role of our phase lock loop in order to make sure that our controls are synchronized. Because other than that, if it is not a reliable reference voltage, then any additional changes in the phase angle difference between the converter voltage and the grid side might lead to incorrect values of active and reactive power, which means you might end up with unacceptable or undesirable exchange of power between the AC side and the DC link. And that may lead to instability and subsequent trip of the unit. Basic block diagram of a voltage source converter. If you have DC voltage control, the current control method, in order to make sure we are not violating the maximum current rated current of the converter. Active and reactive currents are the outputs of our either DC voltage or active power controller, or Q or AC voltage controller. If by any because of any disturbances or any transients, the reference phase angle calculated by our synchronizing mechanism is containing an error, then the values that our controllers are demanding from the current control loop, even though they might correspond to the correct values of active power, it may not be translated into an active power because there is an error in the phase angle. So with that introduction, let's go and have a look at some examples. So the first set of examples I'm going to show you are from offshore wind farms with long AC cable interconnections. Darshan earlier showed you a basic scheme of onshore to offshore interconnection over AC cables. If this is less than like 50 kilometers, you may not need any breaking point in between, but there are nowadays some further distances, like we have been involved in projects with over 280 or 250 kilometers distance between the onshore station and the offshore transformers. In that case, you might need some kind of a basically, can I just draw something here? Probably not. This doesn't look, anyway. you might need additional reactive compensation in between. So the cable, the export cable is broken in the middle of the span between the onshore and offshore station. You might have an intermediate station here with shunt reactors, a combination of fixed and variable reactors, so that at different power injection levels, you might need to vary how much reactive power you absorb in order to make sure the voltages are not exceeded. So if this distance is very long, effectively the entire wind farm or the individual wind turbine generator units are exposed to somewhat a large impedance in a sense. And if the network is also in a weak grid condition, meaning that there is so much penetration of other wind farms, or there are so many inverters that some networks are actually observing these days, or at some power flow conditions there is not, because of this additional injection of wind, your conventional generator units may not be required. So if the operator decides to use the renewable injection rather than the conventional generators, then you might also lose the inertia in the area. So you might kind of compromise the phase angle stability of the point of interconnection to the onshore network. Let's see what this means. For example, this is showing the measurements at the low voltage terminals of a wind turbine generator connected 280 kilometers away from the onshore station. As a result of a fault on the onshore bus, it was a solid three-phase to ground fault, and on the low voltage sides of the on the low voltage sides of each turbine, which in the PSCAD studies, as Darshana explained, they have been represented by aggregated units. You see that the voltage doesn't drop to the same level. You have an impedance between the onshore and offshore station, and as a result, you will see the voltage has some residual value. So the controllers and the PLL do have some voltage to lock onto, even though it might be such that they are actually generating our own voltage and locking onto their own voltage. But after fault clearance, if you notice, and we have zoomed out this area, in this particular case, there is a very large or rather large power reversal. It's over maybe 50% of or 60% of active power. Prior to the fault, we were injecting 7 megawatts. Then there is a transient period for over 100 milliseconds that you have a large power reversal, and then the turbine units, the controls take over and try to ramp up the power based on the grid code requirement. So in this case, it didn't cause any problem. But if we look at the internal values, so we are looking at the same measured RMS voltage, active and reactive power. But if you look at the active and reactive currents that are supplied by the converter, the blue curve is the reference. That's what the converter controls are demanding. Whereas if you look at the measured current, somehow the profile of the active current and the voltage seem to follow each other, which kind of as it could be an indicator that there is an error. And now, even though we are trying to regulate active power, but our active current reference or active current measured active current is actually affecting the voltage, which means an error in the phase angle. Your active current now, because of a phase angle error, is also contributing to reactive power and vice versa. And with the same network, with the same wind turbine that we showed in the previous example, now we have a weaker onshore network. With this weaker onshore network, that effect became somehow more pronounced, and that inverse active power absorbed, or kind of because of that error in the phase angle, now it is much more significant. And as a result, you see this here, the DC voltage and the current in the DC chopper. Here, during this, within this range, our controller basically is unable to regulate the correct levels of active and reactive power, or the DC voltage controller is unable to maintain the DC voltage anymore. So that power imbalance is dissipated by inside the DC chopper, and at some point, the energy inside the DC chopper exceeds the threshold, and because it is not meant for operating at 1 per unit for a prolonged period of time, it eventually trips, and a subsequent rise in the DC voltage causes a trip of the entire turbine unit. So here is where the chopper stopped, and the peak of the DC voltage is where you have the DC voltage over the DC over voltage trip at this point, where you see all the currents go to zero. So that is an indication of phase angle instability and the inability of the PLL to maintain synchronism. Now, what can we do? You can provide that phase angle stability by either if we had the conventional generators in the network, and somehow the network had been stronger, we would have had a chance to ride through the fault without tripping, like the previous slide. But another way to provide this stability is to install synchronous condensers on the onshore station, whether it's on the onshore station or to provide that inertial stability or additional inertia and phase angle stability across an area. Depends on, and you have to do specific studies to do that. Sometimes the wind farm developer, after performing these studies and realizing that there might be a risk, they may decide to just consider synchronous condensers for their onshore station so that they do not cause instability for the rest of the network. So with that, when a synchronous condenser, sometimes you need actually higher than typical inertial levels, like with heavier rotors or added flywheels or things like that, to increase the typical inertial constants of the synchronous condensers that are in normal conditions are not meant for providing inertia, rather than providing higher short circuit levels or maintaining voltage. Here you need the additional inertia and somehow to stabilizing the phase angle. You might need a special set of parameters for your synchronous condenser, and the design has to be verified through PSCAD studies. So having said that, with the additional of those synchronous condensers on the onshore station with the same case that I showed you in example 2, now we have a successful fault right through. And you see that the current controllers, even though we still have the same power reversal, but it happens within a much shorter period of time, and then the controls take over and fault right through is successful. Some of the long cable, some of the wind farms with long cable, like over 200-kilometer schemes, they happen to show resonance, physical resonance, based on the impedance characteristics and interaction of the overall impedance observed from the wind turbine and the onshore point of interconnection may contain resonance points, shunt resonance impedances at rather low frequencies, closer to between the fundamental and second harmonic or third harmonic. This was an interesting case for a 200-kilometer or 250-kilometer offshore scheme from the shore, and we observed that the turbines were issuing over frequency trips after some of the faults we tested. And after further analysis, this is this was fortunately during feasibility studies. So during the design studies, this is what we found, and they had to require, and they had to ask the vendor in order to make some changes in their controls or tune their PLLs and prevent that. But what was happening was the overall frequency, the impedance characteristics. So this is, for example, if you are familiar with PSCAD, the harmonic impedance measurement. When we measured the harmonic impedance of the wind farm, there was a very large resonance close to, I think, 70 Hertz or so, or say 50 Hertz or so. And this was a 60 Hertz wind farm. And when connected to the network, the overall impedance we saw that it was showing a resonance close to 80 Hertz. And what was happening then, when we did solid fault tests on the onshore station as part of the dynamic performance test, we saw that the wind turbines and the PLLs were locked onto that resonance point and were generating 80 Hertz voltages. And as a result, the turbine over frequency protection was tripping it. And for some faults, this was kind of sustained for the entire period of the fault. This was a fault for 150 milliseconds, and after four cycles of 80 Hertz, the turbine was tripping. And after, we also found that when we added the synchronous condenser on the onshore side, we were able to prevent that from happening. But the solution ultimately was to approach the vendor and make sure that they would tune their controls first, and then synchronous condenser was there as a backup for other transients that would have caused an unsuccessful fault rate. I also show you a few slides for offshore wind with HVDC interconnection. So the problems with long cables and long export cables with AC option could be avoided with HVDC. With HVDC, you basically are not limited to the length of or the distance between the offshore and onshore station. This is an option depending on the cost. Of course, you're dealing with an offshore converter station with more complex requirements than just a shunt reactor with variable taps. So this becomes a matter of the size and the justification, economical and also technical justifications for building an offshore HVDC station. So if that is justified, then we will end up usually with this general scheme. You have an onshore station, you have an offshore station that maintains AC frequency and voltage for the offshore network, as opposed to typical point-to-point HVDC schemes where you have power control on one station and DC voltage control on the other. The role of onshore station is to maintain the DC voltage and also control AC voltage or reactive power control, and also for grid code requirements, you may also need to inject reactive current during under voltages. The offshore converter maintains AC voltage and frequency. So as a result, when the wind turbines operate in active power control mode, then in a sense, this bus acts or emulates the effect of a slack bus. You basically push the power because the turbines are synchronized to the voltage produced by the offshore converter. Then they can lock onto it, they can synchronize to it with that, and the natural power flow on the offshore network causes the power to go from the AC network into the AC terminals and be transferred to the DC link, and as a result, you would have this power transfer from offshore to onshore through the HVDC link. And similar to what we saw for the full converter-based system, in case there is a fault on the AC network, the offshore network will not be affected by that. There is nothing to communicate this fault to the offshore in order to dissipate that excess energy, excess power imbalance between the offshore and onshore system. There is normally the dynamic brake system or a DC chopper installed at the onshore bus. Well, and how does it help? For example, I will show you in an example shortly. But and also, if we look at the sequence of startup, the DC voltage is maintained by the AC voltage. So you need to pre-charge through a pre-insertion resistance, and then deblock the converter, regulate the DC voltage, and once the DC voltage is regulated, then you can deblock the second converter and then close the breaker to energize the offshore network. And if you look at this sequence in terms of simulations, onshore converter, you see that we then close the pre-insertion resistance, and then converter is deblocked and regulates the DC voltage here, and same quantities happen on the offshore side too. And then we deblock the offshore station. Here is the offshore station is deblocked and is energizing the AC network on the offshore side. And then after that, the turbines are able to synchronize and start pushing the power back to the network. And so remember that I mentioned an onshore AC fault could lead to a DC overvoltage because the offshore converter doesn't know that there is a fault on the onshore side. So here we have an extreme case. We have an extreme case, an onshore fault, solid three-phase to ground fault at the onshore station. The onshore converter injects reactive power mostly and is limited to the full current. So you see that the converter is, even though it's injecting current, but it is purely reactive. And the active power transferred from the onshore station to the onshore network is zero because you have zero voltage and the product of the current and voltage is zero. But the offshore station, the DC power measured at the offshore station is not affected. So where does it? How does it happen? How can this be prevent? How can we prevent the DC voltage from rising? So that's where your chopper or the dynamic brake system absorbs that excess energy and power imbalance. For example, your DC voltage slightly rises, and then once the fault is cleared, the DC voltage controller on the onshore side takes over, and as you can see, the offshore power generation is not interrupted. And another example for an offshore fault. So you see quantities for the offshore station. You have a single line to ground fault on the offshore side. And this will be the last set of slides I show you. I think we are out of time. And the DC voltage, these are the transients that, because of valve controls in the onshore and offshore stations, are disturbed by that. And also the valve currents are limited by the HVDC controls, but then you have onshore quantities. The onshore voltage is not affected, but because of the power transfer from the offshore to onshore is temporarily interrupted. Then after fault clearance on the offshore side, you have power resumption. So with that, I think I hand it over to Darshana again. Darshana. Yeah, we seem to have technical difficulties too. Everyone is okay. Just a sound check because I think I'm not hearing Darshana. Just making sure.
Can you hear me now?
Yes, you can. We can hear you. You were muted, I think.
Oh, okay, sorry. I said a lot of things and I didn't realize I was muted, so I'll go back and be very quick. So I'm going to discuss a specific situation where you are studying a fault on the collector cable itself, right? We said for most of the system level studies, we represent the collector system, we aggregate the collector system, and we represent all the wind turbines by a single aggregated or scaled unit. And we said that it is good enough for most of almost all our studies. But for this particular study, where the fault is on the collector system itself, and as a result of the fault, you have to trip the feeder, right? Now the fault is very close to the turbines. When the fault is that close to the turbine, some of the turbines may behave well, some may trip, some may lose control. So we at MHI for the past 3 or 4 years, our strategy has been for this particular fault study to model each and every turbine without aggregating or equivalency. So we use the parallel processing feature of PSCAD to represent all these turbines as independent individual units. So the issue here is if your fault is on the cable collector itself and you trip this breaker, then the wind turbines gets isolated from the rest of the grid. And if the wind turbines lose control, and like now if you assume that the wind turbines are injecting current to the grid, current to the collector system consists of cables. Cables are capacitive. If you inject currents to a capacitor and the current has no other path to go out, the voltage on the cable will go up or can go up. So the only way to avoid that is for the inverters, the controls to take control and make sure that it doesn't happen, like limit the voltage, limit the power or the current injection. So what you want is this: when you trip the feeder, there will be over voltage for a short period, but you want the inverter to take control and bring the voltage down gradually in a nice controlled manner to zero. Okay. Then if the fault is on one of the feeders, you also want to make sure that the rest of the feeders don't get tripped or lose control. You want them to recover nicely, as shown in this second graph to your right. So for this study, like I said, we model the inverters and the cables in detail without aggregation. So here's another example, like here in this first example, the voltage seems to come down nicely. Second example, it may or may not violate. See, it's different. The characteristics are different. This all depends on the fault type, the protection and control strategies adopted by different vendors. In this case, this left-hand side response may or may not be acceptable. The voltage goes up to about 1.66. It lasts for a few tens of milliseconds. It may violate temporary overvoltage, withstand capability of surge arresters and equipment, and damage equipment. And so similar, the response on the other right hand side, you can see the overvoltage lasts for a little bit of time. So we may have to again go to the vendor and ask them to review this, and maybe they can adjust their overvoltage strip settings, right? Settings where the inverter controls tell the inverter to actually back off and bring the voltage down, may be a settable parameter. So we have to go to after the study, we have to go to the vendor and have a discussion. If you think that this voltage is, if you realize that this voltage is too much and it lasts for too long for your, compared to your withstand equipment or voltage withstand capacity. So that's again a very specific simulation. With that, I'm going to close the presentation and just show you two examples. In PSCAD. So this is the example of a offshore wind farm connected through an AC cable. The onshore system is represented by a Thevenin's simple voltage source, because this is just for demonstration purposes. But if I go inside this page, you will see the cables, the cable connections, the brake arrangements, some of the brake arrangements in the substation, harmonic filters, the shunt reactors, and in this case, two STATCOMs, the STATCOMs that are necessary to meet your grid code from a voltage control point of view. Like I said, the cables can inject significant amounts of reactive power, and you have to compensate both in steady state and dynamically. And here, if I go to the wind farm, the cables, each feeder is represented by an equivalent cable, like equivalence based on the method that I mentioned earlier in the presentation. Then all the wind turbines on a single feeder is represented by an aggregated or a scaled single unit. See, single inverter model multiplied by the number of units, wind turbine units on that feeder. So that's the scaling. So that's an example of a AC connected offshore wind farm. I think most details on the offshore side are included in the model. The AC offshore network is represented by a simple voltage source in this example. We will make this available to you in some form or the other. Then I also have an example, and I think this is already on our website, of an HVDC connected wind farm, offshore wind farm. In this example, we have represented the HVDC link, MMC VSC based HVDC link with a cable of certain length. I can't remember the exact length of the cable. Then we have a 230 kV a system of 230 kV cables and a transformer on the offshore side, and the 230 kV is stepped down to the 33 kV collector system. And we have modeled in this case 2 wind farm clusters, one based on type 3 and one based on type 4. So here's a situation where the wind turbines could be provided by 2 different vendors, multi-vendors. So once again, if you go inside this model, I think this is already available on our website, but I will make this available for download with our PowerPoints and other material of this webinar as well. And we are simulating a fault response on this system. So with that, I think we discussed quite a bit of technical details with Farid. Hope you enjoyed and this was useful. With that, we will end this presentation and see you in 2 weeks' time. And in our next presentation, we are moving from dynamic response studies like wind farms to a discussion of more traditional EMT studies. So the next set of presentations, next 3 presentations would be on traditional fast transient studies. We are starting with switching studies, switching over voltage studies, where we discuss transmission line switching, design of transmission lines and surge arresters. And we will move on to breaker TRV studies and lightning impact over voltage studies. Thank you very much and hope to see you in 2 weeks' time.